Welcome to Innovate and React. I'm Kevin Hares, and today's episode will be about AEM, Anion Exchange Membrane Electrolysis, which might be the perfect compromise between the normal alkaline electrolysis and the more developed proton exchange membrane electrolysis. And today I'm excited to talk to Miriam Hesse and Bastian Kaufmann, who are researchers in AEM at the Hydrogen and Fuel Cell Center in Duisburg, Germany. Thank you for joining me.
Thanks for having us.
Yeah, thank you very much for inviting us.
The English name of ZBT is, I think, a bit more descriptive of what you do, as the abbreviation only contains the fuel cells in German. But let's start with your background. What brought you to AEM and ZBT?
I studied process engineering at Ruhr-Universität Bochum, and I focused on kinetics and reaction during different reactors. And during my master's, I had the opportunity to write my thesis here at the ZBT because I was interested in water electrolysis. And yeah, since then I have been working in the field of catalyst layer electrode fabrication for the Anion Exchange Membrane water electrolysis, shortcut AEM. And yeah, for me it's interesting to work on materials and to improve the reactions of the electrolysis for the production of green hydrogen.
Yeah, and you, Basti?
Yeah, for me it's kind of a very similar career path. So I'm a mechanical engineer, and then during my, I would say, master's, I kind of came to the conclusion, engineering, I'm not the typical engineer. I would like to be a little bit more focused on the research side of things. But of course, you don't end your study close to the finish line. So I was looking around and I found this whole hydrogen topic always interesting, but I had no clue about it. And then I just wrote the guys from the ZBT for a master's. And then I did my student work there and also started my master thesis there, which was not on AEM water electrolysis. Mm-hmm. So Miriam's masterarbeit was the first, master thesis was the first stuff we did on that. I was still working on PEM fuel cells and a new manufacturing technique in that regard. Mm-hmm. But after both of our master theses, which were kind of at the same time, we both started and are now 50% of our group, of the AEM group. So we are 4 people with one group leader who was also our supervisor during our masters. And now I'm mostly concerned with the actual electrochemical testing part and a little bit on the new methods and tricks that one can maybe do to get a little bit more information out of your cells. But maybe we will get there today to be a little bit more clear, not so nebulous about that.
Mm-hmm. Yeah, sure, we can get more into depth later, but it's more like you're doing the testing part, and Miriam, you're doing the catalysis research, right?
Yeah, my focus is on the catalyst layer fabrication, but I also do the material characterization and also the testing of those electrodes. So it's the whole process, I would say.
Yeah, that also emphasizes that the ZBT is doing more than just the fuel cells. Maybe you can briefly tell a bit more about what ZBT does.
Yeah, it's always funny. Maybe a small anecdote on the side, just for the start. We're currently looking for students to work for us. Mm-hmm. And one of the first questions we always ask is, have you ever heard from ZBT before your applications? And most of the time it's not, even if they are from the Duisburg area. Even then and we have another research institute right next to us, the NETS building, which is also more known already. So we are in an interesting position because in this whole academic world we are a little bit less known, but on the other hand we are more known on the industry world, and that's, I would say, really strongly shows or describes what ZBT actually does. So we do a lot of industry near research. We do research that has always the industry application in mind. Mm-hmm. And Zentrum für Brennstoffzellentechnik, our German name, I would say the Hydrogen and Fuel Cell Center tells a bit more because then the hydrogen is part of it. So we have been only doing fuel cells in the past, but right now we are doing like the whole hydrogen value chain, from coming from the storage and the pipes and how we distribute hydrogen to then possible applications like fuel cells for all kinds of scales, up to the electrolysis part, so the production of hydrogen part, which we are a part of. And depending on the group and the task and the scope, the questions change from more engineering focused to more classical chemistry research focused. And that's quite interesting because then you get really heterogeneous teams and a lot of different disciplines working on this stuff. So that kind of makes a little bit of the charm of the ZBT, that we are sitting between two chairs, but actually trying to hold up and to manage. But of course, it also has its shortcomings, especially regarding funding, because we're not so easily funded like the big research institutes. We have like 50% of our funding is based on projects that we write, so proposals we write. Each and every one of us writes like one proposal per year so that we can keep the whole machinery running. And then we have like a quarter roughly of direct industry contracts, which is also interesting. Let's say company XY wants to find something out, and then they know we are experts in some technology or some measurement technique. Then they directly contact us and they directly pay us to do their research. So that's stuff that we do. And then we have some baseline funding from North Rhine-Westphalia. So that's makes up the whole ZBT structure. And we are independent in the sense that we have our own CEO and our own scientific advisory, and we also have a Förderkreis, but the only holder of ZBT is the University of Duisburg-Essen. So they also have a say in us, but mostly we are free to kind of do what we want to do.
Yeah, interesting. So covering the whole hydrogen value chain, pipes, production, but also the application, fuel cells and ammonia we talked earlier about.
Yeah, exactly. So the whole, and more on the engineering side. So we are a little bit of outliers in our sense that we are more focused on typical, let's put it like that, research questions. But also we always try to think our stuff with the real world applications in mind.
Yeah, this is what I really like, why I work at the ZBT, that we do not just look at one scientific question, we have different tasks and look at the whole hydrogen value chain regarding the scientific part and the engineering part.
Yeah, also it's more applied research, as you said, that if you have always some kind of industry partner, then it's not just a basic research. I mean, that's also very important, but it's just a different type of research.
Yeah. And that can also be a blessing and a curse, as all things can be, because in the end, a lot of questions are born by money, and so you have to think about the whole stuff. And especially when we maybe later talk a little bit about hydrogen, even you have always to talk about the money part in stuff, and can not only do the research for the fun of the research. If you want to put it like that. Yeah. But of course, it's also important and interesting to know what the industry is interested in and what they struggle with, or where we can then help them and get their insights from the then actual application and so on.
Yeah, also further data. Then let's come to the topic of this episode, the electrolysis. We had some episodes about electrolysis before, but let's still recap what is water electrolysis and why do we need that at the moment?
I think most of the people who are listening here had it in their school. The simplest idea is that you put two rods of different materials inside of water, apply current, and then on the one side you produce your hydrogen, on the other side you produce your oxygen. So H2O is then H2 and O2. I think that's common knowledge at that point here. But if you want to do it at scale and in larger areas and more efficient, then you have to engineer the boundaries of your catalyst phases, so of your electrodes, where your actual magic happens. But then you also have to make sure that your media gets to where they belong. So in a lot of senses, if we talk about electrolysis, we talk about the splitting of the water at the cathode to produce the hydrogen and at the anode to produce the oxygen. And in some shape or form, there's an ions conducting media between them, which electrically isolates the two reactions from each other. But then the ions can travel from the one side to the other side and perform the other reaction. I think it's quite, in my head, it's not so easy to explain without any pictures. I just realized.
Yeah, but I think for the listener, it should be clear. This ion conducting separation part is also what is special about the AEM. But to quickly also recap, when we're talking about this whole electrolysis, we would like to use ideally renewable energy to have the hydrogen as a storage for renewable energy and then use that to either transport it or store it and then later use it again. And this is why Germany and also other countries are now trying to build up this whole hydrogen economy, actually. For that, we need the electrolysis in the most efficient form, because as you said earlier, we also have to look at the money and have to see that these projects become profitable, and the more efficient the electrolyzer is, the faster they can get their return on investment. And in this episode, we would like to talk about AEM. So Miriam, what is special about this compared to other electrolysis techniques?
Yeah, the AEM water electrolysis is quite interesting because it can combine the advantages of the currently two established technologies. On the one hand, we have the classical, typical alkaline water electrolysis, which has the advantage that we can use cheap materials in the alkaline conditions. And on the other hand, we have the PEM water electrolysis, so the proton exchange membrane electrolysis, which has a compact membrane-based design. And because of that, it can operate very efficiently. But it often relies on expensive, precious metals like platinum and iridium on the anode side, for example. And now the AEM can combine the best of both worlds. It uses also a membrane. In this kind of system, we use an Anion Exchange Membrane, as Bastian already said. And so this system is closer to the PEM water electrolysis, but it still operates in alkaline conditions. So with that, we are able to use cheap materials like nickel-based materials and replace the precious metals. And I think, or in my mind, this makes the technology very promising because we want to scale the hydrogen production, and therefore the cost and the resource availability is very important.
Yeah, and what's also interesting is that right now, if one is interested in the whole electrolysis world, there's a lot of talk about AEM electrolysis because it's a quite young technology in the sense because the membranes were the bottleneck in the past.
Why?
That's a polymer chemistry question. They degraded very, very fast. Apparently, it's very hard to have an ion conducting material that doesn't degrade under the conditions of 1 molar KH, so pH 14. And the first commercially available stable materials are like 4 or 5 years old only. Okay. So and that brought like the whole uprising of the AEM electrolysis part, because the catalysts were also known in a sense because you could use them in alkaline or other materials, but you couldn't combine them because the membrane then would just die under this, especially if you have efficient catalysts. And And right now there are a lot of, or not a lot, but some companies who are building up these membranes, and it's also not so monopolistic like in the PEM world, where it's basically just Nafion, so PFSR, which is commonly known and stable, and is good for the proton conducting, and something like that in the AEM world. We are not there yet, but there are companies who are working on exactly that to have really stable and ion conducting materials.
So for AEM, they are not these Nafion type, and they're not PFAS containing. I think that's also a big advantage, because this PFAS materials, they are also a blessing and a curse at the same time. Yeah. They are very stable and do well what they do, but especially the production of them comes with huge environmental risks.
Yeah, and that's like one of the things why one of the several things why AEM can be interesting. Mm-hmm. And what always, if one asks what's the problem with AEM, then a lot of people have exactly that in mind, that the membranes are not stable, which shifted in the last 2 or 3 years.
Mm-hmm. What are the membranes made out of?
I think it's also a lot of times it's some hydrocarbon backbone, and then that's not my. I would have to really guess. I can kind of identify it, but I can't really talk about it because we don't do the actual membrane research. So it's like we do everything in the AEM world, but we don't do organic polymer chemistry stuff, because apparently that's hard, and we just test them. So we have companies that come to us and want to test or had tested their membranes.
Okay, so but it is a polymeric membrane. It's not like, for example, with the SOE electrolysis, it's not like a ceramic is a polymer.
It's a polymer, yes.
And then to get the whole system to work, similar to the PEM electrolysis, you need to coat the membrane with an active material, which contains the catalyst. Or how is this the electrolysis cell built for AEM?
This is one opportunity for the fabrication methods. In our case, we deposit the catalyst layer directly on the substrate, because the AEM membranes are difficult to handle, so it's not common that we do the CCM catalyst coated membrane fabrication like in the PEM electrolysis, in the AEM electrolysis. And we do not see the need that we increase the anionic conductivity in this case, because during the AEM electrolysis we still use 1 molar KOH solution in our system, and this increases the conductivity, and there is no need to coat the catalyst directly on the membrane. It's also possible to have the layer on the PTL and get quite high performance.
Mm-hmm. What is PTL?
In this case, it's a porous transport layer. For our porous transport layer, we use in the PEM systems, there is often used titanium non-wovens. And in this case, we use a porous nickel or porous stainless steel non-woven as our substrate for our catalyst layer.
Okay, so you have the membrane in the middle, and then you have this porous transport layer on both sides, and then on each of those sides you have then the anode and cathode catalyst material.
But the catalyst, of course, is still sitting at the membrane.
Yeah.
So it's membrane, catalyst, and then this porous transport layer. So it is like doing it directly on the membrane. So the membrane and the catalyst need to be in contact, of course. But in the PEM world, you really need to make sure that you have ionic pathways from your membrane to your active centers. In the AEM world, it's not so big of an issue, as Miriam already told us. There's always ionic conductivity due to the KOH that's abundantly everywhere in our electrolysis. And then it's a little bit easier so we do a lot of spray coating, which is a quite slow process. And if you do slow processes on polymers that like to change their structure during the coating, then they shrivel up, for example, and then you get inhomogeneous layers. And oftentimes it's better to to sacrifice a little bit of contact from catalyst to membrane to have it more homogeneous deposited on the PTL side.
Okay.
But it's still membrane, then the both catalyst layers, and then the PTL.
So I guess these are already some challenges for AEM that you just mentioned, the membrane itself, but also the fabrication of the electrolysis cell. Basically, that's how to get the catalyst perfectly distributed on the PTL.
Yeah.
What other challenges do you see still for AEM? Quick break. First of all, thank you for tuning in. This really means a lot to me. I would like to ask a small favor from you. It would really help if you could follow Innovate and React on whatever platform you're listening. This helps to reach more people and spread the amazing research of my guest further. Thank you so much for your time. Back to the episode.
That's a big one. So the idea to think, okay, which is also nice for us as researchers, and especially if you want to do your PhD in that kind of stuff, because you can find so many different catalytic active materials, but then to think about how we actually get them to where we want them to be, to do what we want them to do, it's oftentimes a little bit more challenging. You can do your base electrochemistry on rotating disc electrodes, where you have a reduced simple system where you only look at your catalyst, but it's not so easy to then get it close to the actual membrane in your cell. For example, if you have materials that are based on powders, then you have to make sure, if you do some wet coating, that your powder dispersion is really homogeneous, that it is stable, that you can then spray coat it, or spray coat is for industry applications too slow, to have it with slot die coating or doctor blading, for example, or roll-to-roll printing, stuff like that. Then you need special inks. Your catalyst needs to be able to stay in dispersion long enough, and then you have to engineer all this kind of different parameters to get your porous but not too porous catalyst layer.
Okay, so that sounds like there's still a lot of potential in many directions for AEM to improve on, because it's not that old compared to other electrolysis techniques.
And especially for us who are sitting again between the chairs to take a material and not only look at their intrinsic activity, to also how we get it into the cell, how much surface area we can get there. And then there are other techniques like galvanostatic deposition, or what we will later talk a little bit more, I think, about that bypass some manufacturing steps, for example, which why we think that they are oftentimes interesting for us. Because the more steps you have, the more errors can find their way into it. So it's not only finding a material, it's also having a material that is capable of handling. Or that we are capable of handling it.
Yeah, definitely. That's also what I had in my research. I did catalysis for amine synthesis, and there was also always a thing to think about, that you can have a great catalyst, but in the end, if it doesn't have a chance to go to a pilot plant or something to actually work in a larger setup than your flask, basically, then it's a nice catalyst, but the application might not happen. And I think that's very similar here, that you can have a great catalyst, but when you can not manufacture some electrolysis cells out of it and later even on scale, then it's a bit far out.
Yeah, exactly. Especially because of the ionomer. This is another challenge in the AEM electrolysis. So the adhesion of the AEM ionomer is less than the PEM ionomer. And that's why...
the adhesion to what?
The adhesion to the catalyst and the catalyst layer.
Yeah, okay.
So basically we have the ion conducting part of the membrane is also part of the dispersion that we spray coat. Then you have like this system of catalyst materials and also conducting ionomer. But if these ionomers, they act a little bit of a binder and glue your catalyst on your PTL, for example, or on your membrane. But if they degrade, then it is a little bit more prone that then your catalyst really moves out of the system.
Okay.
And apparently there it shouldn't be the same ionomer for the catalyst layer than for the membrane, as people find out that there are different surrounding conditions that govern more or less degradation. So that's also, it's not too easy at the moment. Even if you have a normally stable ionomer for the alkaline world, to manufacture it so that it's even more stable for the catalyst world is also another challenge in of it itself.
No,
and they are not really on the market right now. There are some that are claimed to be, it's only for the catalyst layer, but it's far less than who just do the membranes.
Mm-hmm.
Yes, and that's why we are looking for other fabrication approaches, and that's why we now use the deposition-based approach, which has the advantage that we can directly deposit the catalyst on the PTL. And this is for the industry, of course, very attractive because it's simple and potentially scalable.
So that's also what we oftentimes want to do. We want to do simple stuff.
Yeah.
Because we are simple engineers. We don't want to have like 8 synthesis steps and then you have coated your CF nanotubes with I don't know what for spherical stuff, which is interesting and nice to see that it works. But as you mentioned, Kevin, then no one will ever maybe build an application around it, because you can like produce like 0.2 grams in an hour.
Yeah, exactly.
And it breaks as soon as it sees the sun. Then it's kind of a bit challenging.
Mm-hmm. So what materials are you looking at?
We are looking on nickel. So nickel is one of the most relevant and important elements in the system. And people often combine nickel. For example, they combine nickel with iron because iron can further improve the oxygen evolution reaction to produce oxygen. For example, nickel iron hydroxides or nickel iron layered double hydroxides are very attractive at the moment and are often considered as the benchmark material for the oxygen evolution reaction. And another interesting material is also sulfur. So with sulfur we can also change the composition a little bit and improve, for example, the conductivity and the reaction on the surface.
Mm-hmm. So the nickel, sulfur and nickel iron are typical catalysts. What parameters are you then optimizing for when you compare different catalysts and you screen for different materials?
Mostly we look at the element distribution of nickel and iron, for example, and also sulfur, and how homogeneous the catalyst layer is on the surface. And mostly, we do the electrolysis test and look at the activity and the stability during our measurements, electrochemical measurements.
Mm-hmm.
That's also, if one does just in a big asterisk catalyst research on a rotating disc electrodes, then you do like your LSVs and your CVs to get something for the intrinsic activity. You can calculate your Tafel slopes, which tells you a little bit of how active. I try to not use the word active. How much your catalyst really wants to do what it needs to. I know.
Current density.
Yeah, because I don't like the word activity, because activity gets oftentimes jumbled together with other words. I think it's not accurate enough. I always think about it like you have your catalytic material which wants to do the reaction as a part of itself, and some materials want to do more of it and want to do it better because, I don't know, they have their edges are so aligned and they're nice materials, and then the whole complicated chemistry stuff. And the other side is how much of the material is actually part of the reaction. So in a reduced system like a rotating disc electrode, it's quite easy to find out how much catalyst is actually part of the reaction. We call it in the electrochemical surface area. For most materials that's easier to find out. There are methods. For some materials, like Miriam mentioned, this nickel iron layered double hydroxide, it's not so easy because they are, for some methods, you only you need to get to a certain amount of potential, and if you don't go there, they are not conductive, but you need to be below that potential at some points to calculate the electrochemical surface area. So there are problems with that, and now we come in and take our catalyst layer and put it in a real operating cell where we also have the influences of the other electrode that we can't ignore. And we also have the influence of the membrane and the interfaces. And then it gets harder to distinguish for what we are actually optimizing for. Of course, we're optimizing for most current density at a certain potential for the least amount of materials at all times. But I mean, that's the typical engineering question. In the end, oftentimes it's hard to really see that in real operating conditions, because we only measure the current density of the whole system.
Okay, so you're not looking at the cell level, you're actually looking at the stack already.
No, it's cell level, but also the cell is still part, so the cell also consists of another electrode. So for example, if we want to look at our anode and we try to keep our cathode the same always, which is sensible to do, we still measure it. And if there are changes there for some reason, we still measure them, and then you have to distinguish the losses of the one electrode and of the other electrode, and of interfaces and the membrane. So you reduce the possibilities of what one could do, and then you need to do some tricks to maybe get the same information out of it.
And you mentioned also that you used to combine nickel with other elements to, in the end, use less of the active material, right? Or why do you combine the nickel?
Yeah, so nickel is active, but nickel can be more active in combination with, for example, sulfur. And sulfur is interesting because in our projects, together with AEM, for example, in Schwäbisch Gmünd, we had a project where we did nickel-sulfur catalyst layer by electrodeposition. And this was interesting because we found out that nickel-sulfur can influence the electronic structure, for example, and the conductivity. And nickel-sulfur is able to undergo oxidation and therefore increase hydroxide layers on the surface. So in this case, it improves the performance for the oxygen evolution reaction and also for the hydrogen evolution reaction due to the several advantages of nickel-sulfur.
Interesting. So you can use the same material for both electrodes.
Yeah, exactly. We varied the parameter during the electrodeposition process. So for the anode side, we have a higher hydroxide layer on the surface, which improves the oxygen evolution reaction and creates stable hydroxides on the surface. And for the other part, for the cathode, it also improves the hydrogen evolution reaction compared to when we only have a nickel hydroxide without the sulfur. And this is because during our electrochemical characterization and using impedance spectra, for example, we observed that the electronic conductivity with sulfur is better than having only nickel on the cathode side.
Yeah, and sulfur is also a relatively cheap material, so if you can use that instead of some iridium, then that's also
exactly. Exactly in the comparison to iridium.
Yeah.
And so if this whole electrolysis part gets big and AEM electrolysis gets big, one should have some shares in nickel, because nickel got I think nickel already got expensive in the last couple of years.
Yeah, because of the batteries.
And we will not change that. That will keep on rising up. In a lot of sense, it's always nickel, and you bring other materials inside of it to change how the nickel is structured. And you can also, for the HER, so the hydrogen evolution side, you can also lose cobalt-based stuff or iron-based stuff. So we also have currently a project that tries to synthesize very different kinds of materials or from different kinds of elements, or producing high entropy alloys, so materials that have one phase and are a mess out of different other materials, and to see which materials and which combination really like each other to do the reaction. But in a lot of sense, it's still nickel-based materials, and you can do already great stuff with nickel-based materials, especially nickel-iron-based materials, which is nice because in the end, so there's research on that the iron promotes the reaction. And it's in a sense, if you're an analytical chemist or really want to do your electrochemistry rigorously, you want to make sure that there's nothing else floating in your electrolyte besides the ions that you need and then your catalyst materials, which is far from the actual world later on, where everything is contaminated with iron because the whole system is built up out of iron. And it's good to see that the iron helps the reaction. But also the iron can also lead to some kind of poisoning of materials. So again, that's a balancing and degradation question, which hopefully will not be that big of an issue in the AEM world like it couldn't be in the PEM world. So platinum poisoning based out of iron contamination is a common problem in the PEM world.
Okay, but when you don't have the platinum, then
no,
it's not a problem. And in this case, it seems to even improve the reaction. But what are the benefits of the sulfur? We already mentioned that you can have both electrodes with it. So I guess it's also a manufacturing advantage when you have one material for both sides, right?
Yeah, exactly. This is one big advantage. It's cheap for the fabrication process. And for the scalability for the industry, it can be easily synthesized, and we can control different parameters to tailor each reaction. And so this is why we now want to further investigate and improve the different parameters for the electrodeposition and see how it works in the water electrolysis, and especially how stable this material is, because now we know, okay, it's active. The deposition method is quite simple, but we now want to investigate how stable these materials are under long-term operation. And long-term operation in this case means 100 hours or maybe more, but first 100 hours.
Yeah, but that's already, compared to a very simple lab setup, it's quite a lot. But to what numbers do you need to get to for like larger scale?
That's like always the typical question, and that also the answer to your question a couple of minutes ago. What is one of the hindrances of AEM? That there isn't as much long-term data on it, and that people, and especially companies, are still a little bit hesitant to invest in that, and then also to share the data, how good their electrolysis system that they built up or that they bought is performing under these real-world conditions. Of course, you want to, if I'm not mistaken, like your typical alkaline water electrolyzer, they run for like 30,000 hours or stuff like something like that. There you can change like one of the parts of one of the cells of the electrolyzer, and then it keeps on running. These kinds of data don't exist for the AEM world yet, but there are some publications that are claiming to have done like 8,000 hours or close to 10,000 hours, and showing that the membrane materials especially can stay stable, that the catalysts are stable. But we hopefully, so most of our tests are like 1 week long currently, which is like close to 200 hours. In the future, we also aim to do 1,000 hours, but one needs to make the time for that because it's basically a month, and then you can't do any other stuff, and then you really want to make sure that everything is right. That this, what you want to do, is really important that you do it. But these kinds of data in actual systems are still quite rare. You can oftentimes do a lab-based setup where you have it in your lab in the corner, where you have like only your beaker cell, for example, where only your catalyst is running in there, which is doable, but as soon as you get a little bit larger and the whole stuff, then it also the safety is then the issue, that you don't blow anything up and stuff like that.
And then you really have to know what question you would like to answer and what all the parameters are, so that you actually run this experiment and in the end have some conclusive data and not just some data.
Yeah, that's also a big topic that a lot of people are coming to us, and that we are also interested in, is these called AST protocols, so accelerated stress tests, which are common practice in the fuel cell world and also in the electrolysis world, and also in a lot of other fields of research, that you do some kind of stress to your system, that you know that this stress is the same stress that the system would see after tens thousands of hours. So that's always a big question, and we are focusing a little bit also on that to early on stress your system, that we can later on maybe get to see the same influences. And also the research for that is really interesting, but again, not really people do it because you need a lot of time.
No. And also you need to link your accelerated data to the real life data that you want to emulate, I guess.
So we in the past we had like research partners or companies, for example, for alkaline electrolyzers, that came to us and said, here you have like 10,000 hours of data, try to fit a model, and then try to do some protocols that try to mimic these losses. So that's also ongoing research, which is really interesting, but you need the data, you need the long-term data, and then you need the accuracy of the data, and you need more than just two numbers to really get information out of it. It's not too easy.
Yeah, and regarding the stability, so we do the long-term measurement, but to really understand why these materials work or are stable or are not stable in our system, it's also important that we need to analyze the used materials and then ask ourselves, okay, what is the real active site now, and why is the system running, or why does my material degrade during the system? And this is also something we try to work on to compare. This is also something we do, so we compare the fresh material after our synthesis and the material after our long-term measurements to understand why, or to understand where are the real active sites.
So it might change during the electrolysis process, and then you have basically a different material that just basically in situ generates itself through the process.
Yes. Okay. Yes. For example, for our example, for the nickel sulfur catalyst, we observed sulfur leaching during our measurements. So we have a higher sulfur amount in the electrolyte system. This leads to a higher surface area on the one side, which is good because this improved our activity. But we also want to avoid metal ions in our system, which maybe could also be a reason why our materials degrade during the time.
Because of other metal ions that react with the sulfur?
Yeah, for example, yeah.
Yeah, interesting. And where do you see the anion exchange membrane research going? Like, what do you think is now, from all your results, the next step?
If you look for us, for example, so I would think we are, on the one hand, it's always interesting and important for us as we're looking on the real world systems to distinguish the losses and to really link the losses with ex situ data. So that's what Miriam mentioned, like measuring sulfur content in your electrolyte afterwards, or doing REM EDX measurements, like how your materials change. And we are capable of doing that, so that's always good to have everything regarding of that in-house to see how stuff changes after a certain amount of times or certain amount of stresses, but also to employ some tricks so that's like one of my favorite topics, to distinguish the losses is to reintroduce a reference point into our cell system. So as previously mentioned, we measure the current or the voltage between anode and cathode. But to see only the anode, then you would need another reference point, or so-called reference electrodes, as is common practice in lab-based stuff. But that's not too easy to do on a real cell system, and we are also looking into that to reintroduce a reference point that we can only measure the anode losses and only measure the cathode losses, because then we can be more certain that actually our new material degraded or did not degrade. So even if we now see degradation in our cell, we can't for 100% be sure that it's the new material that degraded. It could also have been like
some
the other electrode. And that is an interesting topic that we are putting some effort into it to really do that. Not only we are interested in that, there are a lot of people interested in that, especially because right now, I would say the basic research can be done still, the lab-based research, but the focus more immensely shifted to the industry near research, because we know that AEMs are stable, and we know that you can manufacture stable catalysts that are active, and of course you can improve on the catalyst materials, but to really now how they perform after 1,000 hours on a river, that's the stuff for the whole community, and then also for the industry. So I think there's a big shift coming, or an even bigger shift, that these are the big problems to translate your lab-based work into the real world, which we also want to do this year with a greater focus to see, okay, we now only take like one catalyst material and put it on a reduced rotating disk electrode setup where we can do typical catalyst research. Then we apply it to a PTL and do like in beaker or flow cell measurements, and then later on put it in the cell to see how the basically same catalyst material changes at each step of the transfer line. So as we get closer to the industry, how does this particular catalyst that we then will be using changes or behaves differently, and what can we already see in the small world, which is then also be true in the big cell world. And I think a lot of people are coming more to that, to do more application near research in the AEM world.
So basically bridging the gap between this lab and industry setup, and you do all of it, as I understand, so you can basically take one material and scale it up from very small applications to bigger applications, and see if the experiments you get in the beginning are still true in large scale.
Yeah, for example, something now we get a little bit into the nerd shit, but I have to do a little bit of nerd shit. Miriam already mentioned it briefly. It's like impedance spectroscopy, so electrochemical impedance spectroscopy, or ICE in short, which is like a really common electrochemical characterization practice where you apply, you have your system under load, and then you apply alternating current on it, and then different parts of your system behave differently to the current, which is also sweeping in frequency. So that some parts then act as a typical resistor, or some parts act like a capacitor, and then you can like kind of map out your electrochemical cell as a part of just regular electrical components, which is common work. But then there's a little bit new, more mathematical approach, which is then called distribution of relaxation times, where you look at your losses based on their characteristic frequency, how they arise during the impedance measurements. And
losses from the material?
Losses from your material. So you can then see that your actual charge transfer resistance, so where your charges, so your actual reaction happens, how much of the overall losses are from that. And then you can, if you have really good control over your system, you can see both electrodes at the same time, that they have distinct characteristic frequencies. And then you have other processes that also have distinct characteristic frequencies. For example, everything media based for like water or oxygen or hydrogen transportation is it's a slower process than ion conducting processes or the charge transfer process. And then you can map that out. And that also gets more attention right now in the world of catalyst research or electrolysis or fuel cell research. But there's a lot of stuff that one can still do, which then gets interesting, and that's like the stuff that I really like then, because it kind of feels like voodoo in a sense, and a lot of people are, especially because of that, afraid of it, and because it's a lot of math that no one really understands who isn't a math person. But I think there's a lot of potential to get the insights if you have good knowledge about your system. And that's, for example, would be then interesting if we do this transfer study from the RDE to beaker cell and then the electrolysis cell to see how these losses, which are associated with peaks, change then, or if we can identify the same peaks at the same frequencies, or how that turns out. That, I think, is an interesting question that I want to do, or we want to do later this year, for example. And there's
so also improving on the measurements and the data you collect to more deeply understand what the actual degradation processes are, for example.
Yeah, and especially in combination with degradation, I think it's interesting, because then you take some ambiguity out of it. And so if we look at degradation in electrolysis cell, we look at the degradation rate, so how much voltage increase you have over time. But that's like one number, then you don't know what actually is making the number go up. And then, for example, with this distribution of relaxation times, one can see that some peaks stay constant, but some other peaks are shifting in time and also shifting in magnitude. And if you have good knowledge about your system, in theory, you could really identify like then the degradation, say that the degradation is based on this, and sometimes maybe have an idea of the process that causes the degradation. But then, as Miriam mentioned, you need all this ex situ stuff as well to link that.
Yeah, super interesting. Okay, great. Then we can come to the closing question. That is, what is your favorite discovery in chemistry? And since you both are chemical engineers, I would also let some engineering questions count.
Well, I really struggled with that one, because I expected of myself that I would have an answer, but so that there are these obvious answers like vaccine, antibiotics, Haber-Bosch, but they don't really capture for me. Now it's a little bit on a tangent. I can tell you what I think is the most interesting question. But not the more. But that's like conscious science and philosophy. It's not really chemistry or nature science anymore. But a little bit also that, because it's a lot of psychology stuff inside of it. But I don't have any good answer on the basics chemistry or engineering. I don't know.
What comes to my mind is that we are able to fly to the moon, for example. So this is something I find really impressive, that we are able to do so.
Yeah, that combines a lot of engineering, chemistry, and all kinds of science topics.
But what is yours? What would you say as a chemist? What is your favorite?
Yeah, mine is the Haber-Bosch process. You already mentioned that's one of the big ones. But I've already done also one episode about the history of it and some other episodes on ammonia and stuff. And it's just impressive, because basically without this process, we would have about 1/3 less people on the planet. That's quite impressive.
Maybe now you got me thinking. Maybe one of the engineering parts, which is interesting, which is more physics, is this whole RSL. So like, who built the chip manufacturing machine, which then on I don't know what kind of scale is able to produce the chips the processor that we need and really use that TMC can build and stuff. That's really crazy. That is really crazy engineering stuff that they got that working. That's insane.
Yeah, these machines are crazy. They're so precise.
Yeah, that's
that
insanity.
Even normal lasers are not precise enough.
Yeah, and I think that's an underrated engineering feat, maybe.
Okay, then thank you very much for joining me. There was a lot that I learned about AEM and the research about it. Thank you very much.
Thanks for having us.
Yeah, thank you again for inviting us.
Also, thank you very much for listening. Please don't forget to follow Innovate and React on wherever you're listening. This really helps the show to grow and get new exciting guests on to continue. Check out the show notes to learn more about ZBT and their research in hydrogen technologies. And if you would like to talk about your research or startup on the show, contact me on LinkedIn or send me an email to contact@innovateandreact.com. Until next time, keep innovating and stay curious.